All right, welcome back. This is continuing on with chapter one, and I call this part two. And the idea behind these sections, we're going to kind of dig in a little. Oh, what a crappy graphic! I'm sorry about that. Uh, it looks all right in normal mode, but anyhow, uh, the idea is that we're going to look at details about how to come up with a the scientific method. And really, out of this one slide, one of the key things here we want is the fun is formulating the question. And a lot of this could be using intuitive type means or observations that you've made. And then you can kind of do some background research to see if others have done it. So you can refine your question and that sort of thing. Then you construct a hypothesis. The fun is testing. I can't tell you how many times I could not wait to come into the lab and see what the results were based on something I was studying. And I really hope someday that you get the same opportunity or experience. You already may have, but for the most part, it's quite fun, I feel. So here's a better slide. So you make an observation and you write a hypothesis proposed. You make a prediction based on some experiment you want to conduct. You get the conclusion, which is the fun day. It's like Christmas to me. And you look at the conclusions and you observe them and you refine your hypothesis if you need to, or you just write it up. And the idea that if you're right, others will reproduce your work. See, it's the test of time. That's really, unfortunately, there is no real a buzzer goes off and yeah, you got it right. Now, you don't know until others either can't reproduce your work or they get different results or find exactly what you find, which is really nice. So scientific thinking is based on experience, observation, and a little bit more than that. It can be intuition. It can be just the gut feel about something, which is the creative part. And uh, and one of the things I do want to mention here is empirical. The key element of scientific thinking is that it's empirical. It's based on experience and observations that are rational, testable, and reproducible. And that's what is what you want, at least from a basis or a foundation. You want to have facts, some sort of something you can hang your hat on. And the other, of course, is it's self-correcting. We continue to make new observations and you refine your experiments. So you dig deeper and deeper into what's going on. And you have to be unbiased, yeah, and you just let the results speak to you. Um, the other aspect is that it's adaptable. In other words, we need to see how it applies for this. Then you can change your hypothesis for a set of other conditions, and it's really interesting to do that. So too many people consuming Echinacea extract seems to reduce the likelihood of catching the common cold or the duration of a common cold. And I have to admit, I've taken some, and you go and you do, and it's definitely testable. And so we make the observations and things, and you formulate a hypothesis, and of course you make a testable prediction. And so one of the things that's kind of devoid in the literature these days are really sort of negative papers. In other words, we did this research and it did work. And it used to be when back in a couple million years ago, when I was doing research at the university, that a lot of times you read a negative type paper, and I just call it negative because it's negative research. It didn't work, but they saved time for folks that might be wanting to go down that path and would choose not to. But you don't see those papers anymore. You just don't. So the idea is A null hypothesis is a negative statement proposing no relationship exists. These hypotheses are equally valid and they are easier to disprove, and that way you can shift to an alternative hypothesis. So if the experiment didn't work, then you shift to um, the null hypothesis. So echinacea reduces the duration and severity of the symptoms of a common cold. A null hypothesis is that the echinacea has no effect or duration, and so it has to be one or the other. It can't kind of be in between. So hypothesis it reduces the likelihood of catching the cold. Echinacea has no effect. So those are the sort of the angles that we're looking at when we do the experiment. Some scientific questions are called causal, lead to hypotheses about what's responsible for observed phenomenon. Echinacea reduces the likelihood of catching a common cold and duration. Some scientific questions are descriptive. They can lead to interesting discoveries, not answerable by a hypothesis. What is the range of a bald eagle? So those are the kind of the things. So a hypothesis is a proposed explanation for an observed phenomenon. And it's measurable, testable, reproducible, hopefully, and contains an independent and dependent variable. And we're going to talk about that. We talk about it in lab too, but an independent variable and a dependent variable. Those are important to distinguish. So here is devise a testable prediction. Propose a situation will give a particular outcome if and then, if this, then that. So you'll find yourself making if-then type statements. So likelihood of catching cold lower or higher, duration is shorter or longer, and so those are good ways to kind of frame a hypothesis and a prediction. So here's another example. Echinacea reduces the likelihood of catching the cold, and here is the experimental design. We have 4 groups. One gets 1 echinacea, one group gets 1 placebo, and 2 groups get no treatment. You get a virus exposure, and treatment after exposure is 1 echinacea, 1 placebo. Whoops, go back. 1 echinacea tablet daily and 1 placebo tablet daily for those who didn't get treated. That would be interesting to see what the results are. So the idea is you conduct the experiment. You have ways to conduct them so that the eyewitness testimony, as an example, the results should be clear. Having eyewitnesses not always reliable, and so what they're trying to do is to look at ways that may not be as good. They know that when people are saying, "Oh, that was definitely the person that committed that crime," and a lot of times it turns out it's wrong, and they've conducted experiments on that, and that was quite an outcome of that. So the experiments are critical, and they show what might happen. So you look for patterns, you determine the findings and conclusions, and if you need to adjust your hypothesis, then you conduct further experiments. So like the criminal identification, they actually did an experiment where they set up a faux crime. It didn't tell the people that witnessed it, and they set it up such that they knew all the details, and then they asked for the eyewitness testimony, and boy, it was all over the place. So they suspects were viewed in a lineup. Witnesses wrongly identified the criminal about 33% of the time. When suspects were viewed one at a time, witnesses made a mistake identification less than 10% of the time. So eyewitnesses aren't the best reliability. So does echinacea help prevent the common cold? Here's some results. Here's the group 1. They got echinacea before, and the duration was 3 days. A placebo before and after 3 days. Echinacea after exposure 3 days. It looks like it was a waste of money all the time I took this stuff, and so maybe the amount of echinacea given this, maybe we have to give them a couple gallons of it or something, or the length of time. But we can revise the experiment. Echinacea protects people from catching colds and reduces is not correct. So further experimentation might alter the amounts, and outcome of these studies illustrate that the results of critical experiments have been gathered and interpreted, and they're still selling this stuff. So cold claims have been studied. A lot of the studies, if you look at these, you have the power to say, okay, did they, what kind of reporting did they do? What was the sample size? And how did the results actually turn out? And so random control trials are always good. And if it's a double blind, in other words, the patient nor the doctor knows that who's getting what, those are usually the best, because there is a placebo effect, and that comes really back from the time, and they've actually run this on TV shows like MASH, but it actually did occur where they ran out of morphine during a big engagement in war, and they were going to the MASH unit and without morphine. So the doctors suspected, well, what we're going to have to do is to come up with a placebo story, because we don't have any of the actual medication. And it's amazing how powerful our minds are over our bodies, because a lot of them reported that their pain went away or was greatly reduced, and all it was sugar. So the placebo effect is real. When do hypotheses become theories? A hypothesis is a proposed explanation. Theories are not speculation or guesses. They are hypotheses which scientists are most certain. They're repeatedly tested, and usually are broader than the scope initially. Scientific theories do not represent casual guesses. That's the key, and so we make observations to conclude those. Scientific theory is an explanatory hypothesis for a natural phenomenon, and we can come up with tests, and it's more than just a theory once things are tested and they turn out to be positive. So we're going to talk more about these things in chapter 4 and 10. The cell theory: all organisms are composed of cells, and cells come from pre-existing cells. And the theory of natural selection. All these sorts of things we can talk about as far as how they work out. So controlling the variables makes the experiments more powerful. You got to be careful on how many variables you run in an experiment at a time. You can isolate those experiments, just test one. That way you can see the causal relationship it does. If you run too many variables, then you don't know which of the variables is actually being effective for whatever it is. So the treatment is experimental condition applied. Experimental group is the individuals who are exposed. The control group are usually treated identically, but they're not exposed to the treatment. Variables, characteristics of the system that are subject to change. So we have dependent and independent variables, and so the dependent variable is dependent on the independent variable. So if you follow me on that, I'll talk more about that here in a little bit. So the most important feature of a good experiment is controlling variables. So you want to minimize any differences between a control group and experimental group as best you can. So here's a study. Vitamin D is a cause of specific death. Systematic review and meta-analysis of observation cohort. In other words, it's a data mine study and randomized intervention. And so what they ran with this is vitamin D and specific death. Poor experimental design can lead to flawed conclusions, which is terrible, because the treatment with, let's say, having an ulcer, and they said, well, if we just put it in a bag, refrigerate, and uh, and let it go into the stomach, then it would get better. And they did this without controls, and they published the data, which is amazing. They said 100% of patients experienced relief. Because all subjects experience relief, it's tempting to conclude that the treatment worked. But there's no controls. We don't really know. But if you do it with a control, 160 individuals, 82 received the experimental treatment, and 34% patients experienced relief. And a balloon with room temperature fluid, so we have one that's refrigerated room temperature, was 38% experienced relief. Compared with the proper control, gastric freezing didn't confer any benefits at all. So you can see how important controls are to really discern the details of a study. Now, I've already mentioned the placebo effect. This is a phenomenon in which people respond favorably to any treatment. And the placebo effect highlights the need for comparison of treatment groups. This is really a problem. And a lot of times when doctors perform studies, they want to make sure you as an individual that may be in that study are not taking other types of drugs or medications that could give you somewhat of a placebo effect or could be influencing the outcome. So clever hounds influenced experimentation, and a lot of times there's sort of the unspoken things or communication that goes on. I didn't say that I was actually giving you the medication, but wink wink nod nod, then the patient knows, and then benefits may pursue. So here is blind experiments, double blind experiments, and randomized. A blind experiment is experimental subjects do not know, but the doctor does. A double blind means that the subject nor the doctor know. So it's kind of that way. There's no wink wink nod nods and that sort of thing. Randomized, experimental subjects do not know which treatment, if any, they're receiving. And it's just totally random. And again, nobody knows. And it's by design. So to draw conclusions from experiments, it's essential to hold constraint to those variables we're not interested in. Ideally, control and experimental groups should differ only with respect to the treatment. Difference in outcomes can be attributed to the treatment. So arthroscopic surgery for arthritis knee. I was a sucker for this. How could you determine whether a particular surgery is beneficial? I mean, it even makes sense to me to do a less type of invasive procedure. So we have three treatments: arthroscopic surgery with debridement, arthroscopic with lavage, and placebo. So lavage is where you're kind of washing it out with a sterile saline. Debridement, you're kind of cutting things out during a surgical procedure. So how does the general scientific, let's say particularly among non-scientists, the volunteers in the study help in advancing our knowledge? Well, how did the researchers decide whether the surgery was effective? If you look at the cutout, they had 51% plus or minus 23. A lavage, where they use a saline solution, and so what you saw was placebo. These treatments using these types of techniques were no better than a placebo, and so you can kind of conclude, nah, I don't think so. So in a well-controlled experiment, researchers can demonstrate that arthroscopic knee surgery for osteoarthritis was no more beneficial for patients in terms of knee pain and knee functioning than a placebo. So it's good to know. Save the money. We got to watch out for biases. Yeah, there's biases. The percent of, boy, we see it a lot these days, but percentage of papers published with female first authors. When the sex of a leading author was known by the reviewers, fewer papers by women were accepted for publication. Well, that's nasty and that's ugly. And those people just need to be moved along. The ones that review those that have those things. But anyhow, so you can look at the idea, but unfortunately these sorts of biases do occur. Uh, so the key in any experiment, the real important aspect of an experiment is the replication, being able to reproduce the study. If you can't, then there's a problem. And so it doesn't matter who conducted it, what country conducted it, what kind of funds are being used. In other words, if you show some negative stuff, are you going to lose your funding? That sort of thing. And that can influence biases, which is our behavior, including our collection and interpretation of the data. It's the thumb on the scale type of deal, you see. With careful controls, it's possible to minimize. In other words, it's just if they report the actual data, bias cannot play a part of that. We have ways to visualize data. This is sort of the fun part, but it also means we have to interpret it. We have bar graphs, line graphs, pie charts, and it really depends on how we want to display it. The line graph is one that you can do like a linear plot, or you can have a logarithmic plot. Depending on how much data is actually changing, we can choose. But the common element is the title is across the top. The y-axis is going up and down. That's the vertical axis, and the axis must be labeled to include the units of measurement. So in this case, it's the performance of midterms, so those are the grades. And the dependent variable is a measurable entity whose response is created by the process being observed. The value is expected to change in response to the independent variable. So the dependent variable depends on the independent variable. That's, I don't know, that's how I've always remembered it. So we do that on the y-axis. Now the x-axis is the horizontal, and it's labeled, and the independent variable is measured entity. So what we do is we put the independent variable that affects the dependent variable, but we always put it on the x-axis, and we can see that, and then you see the data points, and then you can fill the lines in from that. Now you can do linear regressions and things using statistics to make that a straight line, but it depends on what you're trying to achieve. Don't forget, when you do these sorts of things, yeah, you can fudge data a little bit, and I just give you the good and the bad and the ugly. I don't try to cherry pick data. So the visual displays of data generally has few common elements, and the x-axis we use for the independent variable, and the dependent variable we use the y-axis. We always label them clearly and use units that are equidistant and progressively. So let's review. Independent variable is some measurable entity that's available at the start of the process whose value can be changed as required. Dependent variables are created by the process being observed, and those values cannot be controlled. Okay. How can a graph be misleading? Well, you can have ambiguity in the labeling and scales, incomplete information, so you don't fill in the dots as well as you could have. There's bias or hidden assumptions in the hypothesis or how the data is read. In other words, let's say rats usually develop cancer, which has actually happened at Monsanto with Roundup samples, and so they never conduct an experiment over a certain amount of time because the rats or whatever they're testing usually develop a cancer, and so that way they can say that they never developed any cancer. Well, they didn't let the organisms live long enough to develop the cancers, because they knew that, and that's bias. That's also hiding assumptions that they didn't share with the readers. Insufficient, inappropriate context for data presentation, or lies, damn lies of statistical manipulations, just like Mark Twain said. Visual displays of data which condense large amounts of information can aid in a presentation, which we want large amounts of data, good sample size. Then just display the data and it'll fall out. Does it work or not? So the idea is you want to expose the truth, and that's the key. Statistics can help us make these decisions and gaining sort of a trend. You see, average female is 54 inches plus or minus 2.5 inches. The average male is 59.9 inches plus or minus 3. And so you can see the level of error and that sort of things, but we can draw conclusions. So does having access to textbooks help students perform better in class? Students had access to textbooks scored an average of 81. Students that didn't have access to scored a 76. So plus or minus 7%, which 10% would be 7.6. So we're looking at really the error is kind of overlapping a little bit there in my view. Drawing conclusions based on statistics, the greater the difference and smaller the variations between the groups, the more confident we are. So we can see a wide distribution, or you see a sort of a lopsided type. And so statistics can quantify and summarize large amount of information, making us easier to draw conclusions and more accurate ones too. So statistical methods, the greater the difference between two groups, 95% versus 60% is a greater difference than 81 to 76. So yes, as I mentioned, the error kind of made these two numbers almost the same. But if it's 95 versus 60, it's clear, and error is not a factor. So that's what this is saying. So statistics can help us identify relationships, and is the correlation not something that's really the cause of whatever the changes are? So statistics gives us the probability of 95% or 80% or whatever it turns out, and these are the amount of these and out of the outside, the extreme edges are really informative in terms of the shape of the curve, and we can make conclusions based on that in statistics. And again, it's just a tool that we can look at. Pseudoscience and anecdotal observations often lead to people who believe that links between two phenomena exist, where in fact there is no such link. So the bulk of the things that occurred in the distribution really dictate if the data is real or not. The scientific method is above all empirical. We've already chatted about that. The value, judgments, and subjective information. Science neither generates moral statements nor gives insight to ethical problems. Those are more of the street type of things. Technology is not a science, it's an application of the research. So it's just a kind of a detail. Although the scientific method may be an effective path towards understanding the observable world, it can't not give us insights into the generation of value judgments and other types of non-qualifiable subjective information. So what is life? Try to define it. Well, that's a really tough thing to do because it's complex, and use and transform work and regulation, growth and development, and all of these things are really complex when you start adding them together as living organisms. So unifying themes, we look at some maybe overall trends or some things like looking at the chemical and cellular foundations or the diversity of life or the ecology and how it interacts. It's not easily definable, and we're going to talk about this, and there's some things that you really can't quantify that can influence experiments, and we're going to talk about some of those at a later date. But that's it for this particular chapter. It, as I say, this last part is sort of anecdotal. It's not really, I'm not going to emphasize those on an exam, but it's important that you're aware. Out of this would be the independent and dependent variables are important, and the three different types of experimentation in terms of having a blind or a double blind or having a good overall reliable sampling in the overall test. So review those sort of aspects. I'm not going to be too worried about some of the other details in this. So I'll see you in chapter 2.